Have you ever stopped to think about how your phone unlocks just by looking at your face? Or how a streaming service just knows the exact movie you're in the mood for? Well, the answer isn't magic. It's a technology that's actually inspired by the most incredible computer we know of, the human brain. And today, we are going to unlock the secrets of neural networks.
All right, so here's our game plan. We're going to start with the big idea, the why behind it all. Then we'll take a peek under the hood to see how these things are actually built. After that, we'll get into how they learn, spot them out in the wild where you're already using them, and we'll wrap it all up by looking ahead. Sound good? Let's dive in.
You know, the craziest thing about this whole technology is that the core concept is actually beautifully simple. It all starts with us. The inspiration for this new kind of intelligence comes from that 3-pound universe sitting right inside our skulls.
I mean, think about it. These are things we do without even breaking a sweat. But for a computer, that's unbelievably hard. You can't just write a simple line of code for what makes a face a face. So the brilliant folks in computer science had to get creative. They thought, okay, what if instead of giving the computer a massive list of rules, we could build something that learns from experience just like we do?
And the comparison is pretty wild. It's almost one-to-one. See, our brains have billions of cells called neurons, right? And they're all connected. Well, a neural network has its own version. We just call them nodes. And in our brains, those connections can be strong or weak. Same deal in the network. The connections have weights that tell them how important they are. It's literally like we're building a digital brain, but out of math and code.
Okay, so we've got the big idea, the inspiration. But what does one of these digital brains actually look like on the inside? Let's pull back the curtain and check out its basic structure.
Just think of it as data going on a little adventure. First, it enters through the input layer. That's kind of like the network's eyes and ears. Then it dives into the hidden layers. And this is where the real magic happens. This is where the network sifts through everything and finds all the interesting patterns, the connections that we might not ever see. And then finally, after all that work, one single clear answer pops out the other side, the output layer.
Now let's zoom way in on just one of those nodes. Picture it like a tiny little manager. It's getting information from all the nodes that came before it. But here's the key. It doesn't treat all that information equally. It assigns each piece of info a weight, which is really just a score of how important it is. A high weight screams, hey, pay attention to this, while the low weight just says, not so crucial.
So after it's added everything up, the node has to make a call. Is this signal strong enough to be worth passing on? And that's where this thing called the activation function jumps in. It's basically a gatekeeper. It looks at the total score and decides, yes or no, open the gate and let the signal through to the next layer. And believe it or not, that simple go or no-go decision, when repeated millions of times, is what lets the network learn incredibly complex stuff.
And boom, that's the process. If the gatekeeper says go, its decision zips along and becomes a brand new piece of information for the next layer of nodes. This happens over and over and over again, like a wave of information just washing through the network until it reaches that final answer at the very end.
So we've got the structure all laid out, but a brand new network is essentially a blank slate. It's pretty clueless. So how in the world does it actually learn to do something useful, like tell a cat from a dog? Well, it goes through a process of trial and error, but it's a very, very smart kind of trial and error. It all boils down to this really clever 4-step loop. First, the network takes a wild guess. Then, it checks to see how wrong it was. We call this the loss. The bigger the screw-up, the higher the loss score. Then comes the really slick part. It actually works backward from that mistake, figuring out which of its connections were most responsible for the error. And finally, it adjusts those connections just a tiny, tiny bit, so its next guess will be a little bit better. Now, imagine doing that thousands of times a second. That's how a network learns.
So on its very first try, the network might be way off, getting an error score of, say, 97.4. The entire point of that learning loop, its whole reason for being, is to crush that number. With every single guess and every tiny correction, it's just trying to nudge that error score down, 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 getting it as close to zero as it possibly can.
Okay, I know what you might be thinking. This all sounds a bit abstract, maybe like something out of a sci-fi movie. But here's the thing you have to realize. You have probably used a neural network dozens of times already today without even knowing it. Let's look at where this stuff actually shows up in our world. Right, so not all networks are built the same. You gotta use the right tool for the right job. For anything visual, like images, we use a special kind called a convolutional neural network, or CNN. That's what's powering your phone's face unlock.
For things that happen in a sequence, like words in a sentence, we've got recurrent neural networks, or RNNs. That's what's helping your phone predict the next word you're about to type. And for really heavy-duty language stuff, like real-time translation, we use a fancy kind of RNN that has a much better memory.
These things are already everywhere, working behind the scenes. They're helping doctors spot diseases in scans way earlier than was ever possible before. They are the silent guardians on your bank account, flagging fraud in milliseconds. They are absolutely the reason your favorite streaming service feels like it can read your mind. And yep, they're the digital eyes that allow self-driving cars to see and navigate the world around them. It's a hidden, but totally essential part of modern life.
So let's zoom out for a second. What's the big picture here? What does it really mean for us, for society, that we can now build machines that learn on their own?
Well, like any seriously powerful tool, there are trade-offs. On the one hand, they can spot patterns that are completely invisible to us, and they just keep getting smarter the more data you feed them. But they need absolutely massive amounts of data and some serious computing power to get going. And here's a tricky one. Sometimes they act like a black box. They'll give you the perfect answer, but we can't always understand exactly how they got there. Kind of like a genius who aces the test, but can't show their work.
And this right here, this is the most important takeaway of all. For the entire history of computing, we told computers exactly what to do, step-by-step instructions. We wrote the rules. With neural networks, that whole idea gets flipped completely on its head. Now, we don't write the rules. We just show the machine a ton of data, give it a goal, and it learns the rules all by itself. We've shifted from being programmers to being teachers.
So this leaves us standing on the edge of a totally new era. For the first time, we have a tool that can help us find solutions to problems that we as humans don't even know how to begin to solve. The question is no longer just, what can we build? It's now, what should we teach? What are the biggest challenges, the most important questions that we want our new digital minds to help us answer?